So one of the biggest challenges we're facing from a GSDO logistics perspective is probably inherent to a lot of the development of a new system. And in this our particular case, we're facing a new capability to be able to launch a rocket while we're leveraging off what was existing in support of Apollo and then the space shuttle programs. So as a result, what we face is a combination of new systems and old systems. And old systems are systems like the crawler that's used to move the new mobile launcher that's being developed to support SLS. That crawler was initially developed to support the Apollo program. And while it's been modified many times over the decades, it's still then difficult to try and understand, okay, what modifications have been made? What material do we think needs to be spared for that crawler still based on what it's being used for now? And then also trying to understand what parts can we still find for the crawler in terms of spares, because those type of systems, when they get to that age, it becomes difficult sometimes to try and figure out, well, what spares can we still find or are capable of finding. And additionally, then we also do have new systems like the mobile launcher actually encompasses many subsystems. Those subsystems are subsystems made up of cryogenic fluids, mechanical, pneumatics systems. And so as a result, then we have to go off, and those new systems are still being developed, tested before they're implemented or put into operations. And so as a result, those are still going through cycles of testing and redesign and modifications before we can actually have a final system, which is what we call the as-built, how it's actually finally built at the end. And so during the course of those modifications, our logistics engineers have to try and work with the design engineers to try and understand what is the latest configuration of that system, or what is the anticipated final configuration of that system, to make sure that whatever parts that we actually are sparing or trying to spare, we can actually go and procure, and make sure that we don't procure material that's not really needed or necessary. That way we don't go off and end up with many parts that are no longer needed. One of the challenges that we also do face and are facing with, in particular, the DDT and the design, development, testing, evaluation environment that we're in now for GSDO, is that in the cycle of designing a new system and testing it and trying to do so within a given schedule, you don't have any real historical knowledge as to what the performance of this new system is going to be. All you do know is that you need the parts procured so that when you're going through the testing of this system, that if something breaks, that you have a spare on hand to be able to quickly fix it, so that you don't have to sit and wait, and your whole testing team doesn't have to sit and wait while a new part is procured and arrives and is sent to wherever that area is that system is being tested to. So as a result, what we do is we proceed at risk. We try and say, okay, well, we believe that there's a high likelihood, or likelihood is a relative term as well, but there's a likelihood that you could need additional components or parts or materials or spares for this system based on the testing that we're doing, or just knowledge of what tends to break whenever you're doing a testing. And so then we go off, and at risk we will go and procure some parts, knowing that there's a likelihood that when we go procure that part, if something breaks on that new system, then it could very well be that the system is redesigned. And so as a result, that part that we bought may not be used, but we don't know for sure whether there's going to be a redesign, or whether they're going to just try and fix it and understand, hey, we can proceed with this because the likelihood of this happening again is very small, so therefore we're going to need that spare so that we can fix this, so we can continue with testing. So that's where, from a logistics standpoint, we essentially, again, we proceed at risk and go and procure the item, not knowing for sure whether it will be needed or not, but making sure that we try and preserve the schedule and the process as best we can. I will say that from a logistics perspective, I think one of the lessons learned that we really do want to try and take away from this, because we don't do whole-scale development of a new program often. Most of the time, whenever we go off and we develop systems to support a program like we are doing for SLS, usually those life cycles, or the anticipated life of this particular system is that what we'll be doing in launching SLSs for at least 30 years or so. And so what we see a lot of is that because there's so much time passes between the development of these new programs, we end up losing a lot of the best practices that we tend to understand once we finish development. And so one of the things I think that we tried initially from a GSDO logistics perspective is we initially anticipated, well, development will take care of all of the material that they think they're going to need for testing and development to build a new system, and then logistics operations will just focus on that, on operations standpoint. And so we can expect that development will be able to go and develop a new system, and then once they've developed that system, they'll pass it on to operations, and operations will take, and then we'll run it essentially for the next 30 years. Well, I think what happened as the course of the years went by, we discovered that you can't really, from a logistics standpoint, break the two. Development and operations go hand in hand. A lot of what we initially figure out as to what needs to be spared and what is the best way to optimize the logistics life cycle of a system is by having our logistics engineers get injected and sit next to those engineering design groups to try and identify what is the best from our best knowledge, what is the recommended spares, or what are the recommended material that we can have for that particular system, and to make sure that then we can support it through the development as well as operations. And I think that's one of the larger lessons that we've learned, is that we really need to get involved as early as we possibly can in the development of a new system in order to really have a good, successful opportunity to try and minimize the life cycle costs of a system. So one of the things I think that everybody always associates NASA with is the engineering perspective. I always like to say that logistics is where engineering and business come together. What we really do in logistics is we try and analyze statistically probabilities from a mathematical perspective. We try and analyze what is it that a system is going to need through the course of its life cycle. Then we have to go out into the commercial environment and try and figure out how do we get those parts that we need to get for the least cost that we can. And so that's why I always say that's what we try and do. We try and interface with engineering as well as the business community to try and make sure that, that we can support our goals successfully. So I would say that that is another avenue out there for those kids in particular who want to try and figure out, well, what is it that we want to do and what does NASA do? Well, that's one of those areas that particularly going through college you never hear about is logistics engineering. That's a question I get at a lot of career fairs, is what exactly does logistics engineering do? And that's where I want to say it's not your classical engineering development design type of profession. It's more of a, okay, now that we have this nice engineered solution for what we want, how do we go off and actually go buy and acquire all of the parts and materials that we need so we can build it and successfully launch a rocket, in this particular case here at KAC.